Hello everyone, I'm Typhoon, and in this lecture we will be diving deep into the HTTP packet analysis to gain a better understanding of how this protocol functions. Now, throughout this lecture, we will analyze HTTP request and response packets, understand how web browsers communicate with servers, identify common HTTP headers and their functions, capture and inspect GET and POST requests, and we will also observe how HTTP differs from HTTPS and why encryption matters here. So here we have the web page with HTTP, and we also have the auxiliary caten, for example, with HTTPS. You can see our web browser says this connection is secure, but in this case, connection is not secure. So here, to see the HTTP packets in action, we will capture some packets here. We will start the Wireshark first and select the appropriate network interface card. And here we are. Go here, go to this website, or you can also select another website. In this example, we will also use these features. You can see this is not a real shop. This is example P application, which is intentionally vulnerable to web attacks. So this is just an HTTP website, but this will work in most websites as well. And here we are. Let's stop the capture, and we will add filter for HTTP packets using HTTP. So this will help us isolate only HTTP traffic from other network activity. So here, this capture shows a series of HTTP requests and responses exchanged between a client and with this IP, in this case it's me, and web server with this IP starting from 44 and ending with 3. So this is the first HTTP request from the client. It is like requesting login.php. So this the browser requests a login page from the server using this get method. This request contains headers like host, user agent, and accept encoding. We have the HTTP 1.1 200 OK. So the web server responds with HTTP 200 OK, meaning the request was successful. So this response contains HTML content, like text HTML you can see here. This is likely the login page. So the response size is 2802 bytes, which includes the HTML structure, forms, and scripts. In the packet number 24, we have the HTTP GET request. After receiving the login page, the browser automatically requests additional resources. This is a request from the website CSS file, which style.css, to apply styling. So this request is made via GET, as CSS files are static and do not require data submission. In packet 25, this is the HTTP GET request for images logo.gif. The browser requests the website's logo. In this case, it might be this. Let's actually copy the link. Yeah, oops, no. Copy image link. And here we are, images logo.gif. So this happens because the HTML file here referenced this image. So the request follows the same get format, asking for image file. And we also have the packet 32. This is a get request for favicon.icon. The browser requests the favicon file. So this is the smile icon that appears in this browser tab. So most modern browsers automatically request this file if it exists. And lastly, packet 63, which is HTTP 200 OK response for the basically favicon.ico file. So the web server responds with HTTP 200 OK. So the response contains the favicon file, and the MIME type is image x icon. The size is 1189 bytes, meaning the file was successfully retrieved. So here, in general summary, we will also analyze these packets in detail. But in general, the client requests the login page. Then in packet 18, the server sends back the login page. Packet 24, the client requests the CSS file for styling. 25, the client requests the logo image. Packet 32, the client requests the favicon. And packet 63, the server responds with the favicon file. And now let's open the first packet and see how this HTTP protocol works. Open the get. Yeah, we can make this bigger in this case. So as we did in the previous example, we will analyze this in a very detailed way. We have the frame 12. So this is basically a physical layer. In OSI model, it is layer 1. We have the frame number, size on wire, captured size, which means Wireshark captured the full packet, and interface. So frames are how data is physically transferred over the network, which bits on wire. So Wireshark captures frames to analyze the network traffic. We have Ethernet, which is data link layer 2. We have source MAC address. This is client's MAC address, in this case, our. And destination MAC address. This is our router's MAC address. And we also have so these MAC addresses are used for local communication, which is layer 2. So data is encapsulated in Ethernet frames before being sent over the network. We also have the IP version 4, source and destination. This is our source IP address. This is our local IP address and destination IP address here. This is web server's IP. So we are using the protocol TCP here. Source port 5374. This is random client port, and destination port is 80. This is standard HTTP port. And we also sequence one, acknowledgement one, and length. Ensure reliable transfer with this sequence and acknowledgement data transfer. As you already know in previous lecture, TCP is connection oriented and ensures packets arrive in order. HTTP runs over TCP to guarantee reliable delivery of data. And one of the important here, we have the hypertext transfer protocol. Now that we have covered the lower layers multiple times in our previous lectures as well, now let's dive into the HTTP, covering security, efficiency, and real-world use cases here. So HTTP has several methods like get, post, pod, delete, and head. So most websites use get for browsing and post for login or sign up forms. So get is less secure because parameters are sent in the URL and can be cached. So HTTP is inherently insecure because it does not encrypt data. This makes it vulnerable to various attacks like man-in-the-middle attacks, like a hacker intercepts HTTP traffic and modifies the response, or a fake login page is injected into an HTTP site to steal credentials. We can also do session hijacking with HTTP, like HTTP cookies are transmitted in plain text, allowing attackers to steal session IDs. And an attacker captures a session cookie and logs in as the user. And we also have the data exposure in URLs. This is another security vulnerability, like sensitive data, like passwords, tokens appear in URLs, if you use the get as a login form, like some older websites do, but if you use like login.php, question mark, username, admin, and password, you will easily be like exploited here. if you use HTTP as well. And yeah, in HTTP, which is all, this is all the technology, but in early HTTP versions, every request opened a new TCP connection, which was slow. But this keep alive in transmission here, like allows multiple requests over a single connection, which reduces overhead. And HTTP is also compressible, like web pages and images can be compressed using gzip to reduce bandwidth usage. This speeds up loading times and improves user experience. So now, as we always do with our previous examples and explanations, we will analyze this all HTTP protocol here, packet by packet. So we have the request line. This is the first line of the request, get login.php, HTTP 1.1. So here we are using HTTP method get, which requested a resource. Login.php, the resource or URI being requested. HTTP 1.1, this is the protocol version used here. So the request uses get, which is the most common HTTP methods. Other methods include like post, pod, delete, which you will learn in next lectures. And what we here can see here, which HTTP headers. So we have the host.test.php, vulnweb.com. The request contains multiple headers that provide information about the client's capabilities and preferences. So this host header tells the server which websites the client is requesting. So many servers host multiple websites, like virtual hosting. Without the host header, the server wouldn't know which site to return. We have the user agent. This identifies which browser and operating system the client using. In this case, we are using. Here, the request came from Firefox 135 version running on Ubuntu Linux x86 64 architecture, so basically 64-bit. And there's some security concerns here. So websites use user agent strings to optimize content, but hackers can also exploit this. For example, if an attacker sees Internet Explorer 6, they might launch Internet Explorer 6 exploit. Like basically just Google it. And here we are, like there's so many exploits because this is an older version of Internet Explorer, but I doubt like newer versions do. And yeah, we also have the accept text HTML. So here the browser tells the server what types of responses it can handle. Here it prefers HTML, which text HTML, but it can also accept XML, XHTML, and so on. And here this characters here means it will accept any format, but with lower priority. We have the accept language. So the client requests the response in English. We have this Q equals 0.5. It means also accept generic English, but with lower priority. And so websites use this to return language-specific content. We also have the accept encoding here, gzip, deflate. So the browser asks the server to compress the response before sending it. So gzip and deflate are compression formats that reduce data size, making the page load faster. So benefits of compressing HTTP responses can reduce like data transfer size by 50 or 90%, improving performance. But some compression methods can lead to like attacks if improperly used. And we also have the connection keep alive. Normally each HTTP request opens and closes a new TCP connection, which is slow. So keep alive tells the server to keep the connection open for additional requests. So this allows the browser to load CSS, images, and scripts without reopening the connection. So here this keeps browsing faster by reducing latency, but it can increase server load if too many connections stay open. We have the upgrade insecure requests. This means the browser prefers HTTPS, but it still sends this request for over HTTP. So if the server supports HTTPS, it may redirect the client to the secure version. So this request was sent over the HTTP, not HTTPS, which means anyone sniffing the network can see the full request in plain text. If this were a login request, credentials would be visible. So always use HTTPS to encrypt HTTP requests. And here we also have full request URI. The full URL being requested is this login.php. Since it is HTTP, it means no encryption, which data is transmitted in plain text, and it is vulnerable to man-in-the-middle attacks. So any attacker on the network can capture this packet and see everything, including session cookies. So always use HTTPS, which encrypts the request. So HTTP follows a request response model where a client requests resources and servers return responses. GET requests are used to retrieve data but expose parameters in URLs, which is not safe for logins. So you use the post request for logins if you develop a website. And the next step is frame 18. Will show how the server responds to this request. Now let's open the frame 18 here to see more detailed information. We have the line-based text data. You can see it's basically HTML content. And this packet represents an HTTP response from a web server to a client request. Then now let's break it down step by step. As we always do, we have the frame, layer 1, layer 2, data link layer, layer 3, network layer, and layer 4, transmission control protocol. This is a IP version 4, so it's a transport layer, layer 4. Source port is 80, destination port is a randomly assigned client-side port for this session. So this is a part of the established TCP connection, meaning the client sent an HTTP request earlier, like we analyzed it, and the server is now responding. So here we have one of the most important details in this lecture is HTTP. This is layer 7 application layer. So here we see hypertext transfer protocol has two chunks, including last chunk. So this is an HTTP response with a chunked encoding, meaning that data is sent in multiple chunks. We have the status line, protocol version, HTTP 1.1, status code 200, which means OK. The request was successfully processed by the server. HTTP headers we have here is server nginx. So the web server software handling this request is nginx 1.19.0. We have the date, Sunday, 9 February 2025, the date and time when the response was generated. We have the content type. The response body contains an HTML document, you can see here, text HTML, with the encoded in UTF-8. So the response is chunked. You can see transfer encoding chunked, meaning it is broken into multiple parts and sent piece by piece. Connection keep alive. The connection remains open for further HTTP requests from the client. Powered by PHP 5.6.40, Ubuntu 20.04.1. So the website running PHP 5.6.40 on Ubuntu 20. So this header exposes server-side details, which could be the security risks if an attacker finds vulnerability in PHP 5.6.40. Let's actually Google it. PHP 5.6.40 exploit and .com. Yeah, there are some multiple vulnerabilities. And yeah, here we have the content encoding. The response is compressed using gzip for faster transmission. And we have the HTTP response tracking. So the response took 0.236 seconds to arrive after the request was sent. The original request was in frame 12, which we analyzed earlier. So meaning we can also check the frame 12 to see the client's HTTP request, but you remember it was requesting login.php. The next request and response continue in frames 32 and 63. 32 and 63, you can see. And yeah, we have the request URI here, which is basically the client requested the page on login.php earlier from the test php.vulnweb.com, which is a deliberately vulnerable test website for security analysis. So this might indicate, as this URL says, it may indicate a login page where credentials are entered. Now we also have the HTTP chunked response. The actual HTML response is compared to 2000 like almost 802 bytes, but expands to this 5,523 bytes after decompression. But you can also see this content encoded into the bot, so 2,484 bytes expands into 5,523 bytes. And we have also extracted HTML content here. This is the HTML source code of the page. So this page is still using HTML 4.0.1 transitional standard, which is outdated. So this is an HTTP 200 OK response, meaning the web server successfully processed a request. So the request page is login.php, which suggests this might be a login form. The server is running ng on X with PHP 5.6.40 on Ubuntu 20.04, exposing potential security details. The response is chunked and compressed using gzip, making it efficient for transmission. So the actual HTML source code of the page is included in the response here, meaning anyone sniffing this traffic can see the full page content. Now let's open the packet number 24 and see what's inside it. So again, we have the frame, which is physical layer, frame number 24. The packet was fully captured without truncation. Ethernet, layer 2 data link layer. We have source MAC, destination MAC. This means the packet is traveling from the client to the server as a request. IP version 4, source, this, destination starts from 44, ends with 3. This is the public IP address of the web server, and this is our machine IP address. TCP header 4, layer 4, IP version 4, transport layer. Source port is 53,378. This is a randomly assigned client-side port for this session. We have the destination port 80, the standard HTTP port on the web server. So this is the part of the established TCP connection, meaning the client previously sent a request and now it is requesting an additional resource. Here we are. Now we have the style.css here. This is the CSS file that client wants to download. The full URL here is style.css, like test.php, vulnweb.com style CSS. The client is requesting the resource from this website here. And we also have the HTTP headers here, user agent. The browser uses Firefox 135 on Ubuntu Linux. The user agent header tells the server what browser and operating system are being used, which can affect how the server delivers content. Accept text CSS. The client is specifically requesting a CSS file, but is also willing to accept other types of content if necessary. Accept language, again, it's the same, except encoding same. So the client supports compressed responses, gzip and deflate, which helps in reducing bandwidth usage. The connection is same as keep alive, so the connection remains open for additional requests. We have the referrer. This tells the server that the CSS file was requested while the loading login page. So the referrer header exposes where the request originated, which can sometimes be used for tracking user behavior. We also have the priority u equals 2. This assigns a priority to the request, helping the browser decide which resources to load first. And the full request URI is this. This confirms client is requesting the style.css file from the test php.vulnweb.com. So this is basically an HTTP GET request, meaning the client is asking for CSS file from the web server. The client browser sent detailed information about its capabilities, and the CSS file request came from the login page, which loaded here after getting this here. So the client prefers compressed responses, and the user agent header reveals the operating system and browser, which could be used for fingerprinting users. So we covered the GET and the HTTP, so let's quickly look at these packets as well. And we can also look at this from here, this chain. So we have the packet 24, which is HTTP GET request, which we explained. The client requests the CSS file, requires to style the page. HTTP method is GET. URL is style.css. So the login page likely contains the link tag referencing this style sheet. So what happens next? The server should respond with HTTP 200 here, and in the packet 25, HTTP GET request for image logo.gif, the client requesting an image file used in the website. HTTP method is GET, and URL is logo.images/logo.gif. So this website probably contains an img tag displaying the logo in the login.php. We also have the HTTP GET request for favicon.ico file. The client requests the favicon.ico, which is a small icon displayed in this browser tab here. HTTP method is GET again, and the URL is /favicon.ico. So most browsers automatically request this file when loading a web page, so it doesn't have to inside this login.php. So yeah, we also have lastly the HTTP 200 OK, which is server response for favicon.ico. So the server responds with an HTTP 200 OK, confirming that the favicon was successfully retrieved, content type image X icon. So the payload contains binary data, basically of the favicon, and also another images here. So here, what does this packet capture represent? So this is basically some HTTP communication with this website. So the client requests this login page, the client requests additional resources like CSS and images, and client requests the favicons. So all requests were sent over HTTP, which is unencrypted. Everything is visible in plain text, making it vulnerable to sniffing. The browser automatically requests additional resources like CSS, images, and icons are requested after the main HTML page loads. So if login credentials were submitted via HTTP, they would be visible. If a post request appears later, it may contain username and password in the plaintext. So next steps, what should we look for next? So if some traffic is there to check for security risks, do you see a post request like login attempt? Would you like to check the response for the CSS or logo image? And are there cookies or session IDs being transmitted in plain text? So yeah, that's basically what to check when you see the HTTP traffic first. So again, these HTTP traffic are encrypted and outdated. Some web browsers even give an error when you visit the HTTP websites. So thank you for watching. I'm Typhoon, and I'm meeting you in next lecture.